Log on, tune in, find out. Another good idea from Cambridge.
Will speak to us on an explicit construction of a complex of variational calculus and new conformal algebra.
Since this conference is about algebraic structures arising in physics, it makes sense to say at least a couple of words about how the structures do arise in physics. And the structure that I'm going to explain actually underlies both very important algebraic structures like vertex algebras and Poisson vertex algebras. Actually, it's just part of them. And it indeed arises in connection with at least two physical theories and at least with two mathematical theories. First of all, chronologically, at least the earliest date that I know is 1971, when Gardner and independently Faddeev and Zakharov introduced the notion of local Poisson brackets, and using them they studied the simplest integrable equation, which is a KdV equation. And the local Poisson bracket looks as follows. You take several functions on a manifold, and then you define Poisson bracket of two functions at distinct points x and y to be a certain, say, differential polynomial or more general functions in ui's and the finitely many of the derivatives applied to the delta function. And this bracket should satisfy a certain axiom, which are basically skew symmetry and Jacobi identity. It's on a manifold. X and y are points of a manifold.
So it's some formal notation.
Yeah. Yeah, simply delta of xy means simply that integral of f of x delta of x minus y.
Of the day again.
Right.
Vita, please correct. Write P depending from differential operator, from D.
Right.
D by D. Okay.
Some years later, Belavin, Polyakov, and Zamolodchikov wrote the first paper on conformal field theory. So it was not so long ago, but there was so much done in this area. And the basic notion there is something which is called the operator product expansion of quantum fields. One writes something like this, that if you want, if you have a quantum field phi, say, of x, and another quantum field psi of y, then when x and y are close to each other, you may decompose it as sum psi, say, j of y divided by x minus y to the j plus 1. It took for me some time to understand what it exactly means, but it can be understood in a very rigorous way. And I, for example, explain it in my book, Vertex Algebras for Beginners. Now, psi of this quantum field is the following thing. It's a very simple thing. It's just sum phi n x to the n minus 1, where phi n are endomorphisms of some vector space called the space of state. Now, how the Lie conformal algebras arise from this? The basic notion is the lambda bracket. Namely, you define the lambda bracket by applying to both sides the Fourier transform. It's residue x e to the lambda x minus phi. When you apply to the first equation, you get ui lambda uj equals p u prime, etc. And it's good that Sergei Petrovich reminded me that once you put divisor, you put lambda here. And it is if you apply to the first formula. And if you apply to the second formula, you get phi lambda psi equals sum lambda to the j over j factorial psi j. All things which are in these two formulas depend on y, so you can drop this y. And so you get some operation on the space of classical fields, and here on the space of quantum fields. And it turns out that all of them, that both operations obey certain axioms, which is the axioms of a Lie conformal algebra. So what is a Lie conformal algebra? It is a module D in this picture is just a partial derivative by y. Endowed with a lambda bracket which is certain bracket which depends polynomially on lambda. And notation is that A tensor B goes to A lambda B. Of course, I have to choose which brackets to write, curly or straight, but both satisfy the same axiom. So let me stick to the straight brackets. But of course, when you talk about the Poisson vertex algebra, you'll have to write curly brackets. And for vertex, you write straight. Such that the following, subject to the following axiom. Which are very similar to the axioms of Lie algebra. The first axiom of Lie algebra is just axiom of an algebra, that product bracket should be bilinear. Here it is replaced by the property which I call sesquilinearity. So you have to say how to take D from the first place and how to take D from the second place. Here it is just minus lambda, A lambda B. And here it is D plus lambda, A lambda B. With all these properties, it's very easy, are very easy to deduce using this formal Fourier transform. The second is skew commutativity, which says that if you permute B and A, you get negative A, and here you have minus lambda minus dB. And of course, if you want to talk about supers, then you have to put here a sign parity. And finally, the Jacobi identity, which is that A lambda B mu C minus d lambda d. And again, here you put sign if you want to put that super algebra is equal to a lambda d.
The D is a derivation of R.
Yeah, because on the space of fields, all fields depend on the variable, say y. And there is derivation by y. Derivation of a quantum field is again a quantum field, of a classical field is again a classical field. All right, so this is a definition. Yeah, maybe I should say also, let me say it here. I said that also there are mathematical theories which lead to lambda bracket, and the first of them is just the theory of infinite-dimensional Lie algebras. Of course, the most famous infinite-dimensional Lie algebra is the Virasoro algebra, whose basis is ln in the center, and who obey the commutational relations that everybody knows. I will not write it, but I will write it in a different form. Maybe I will introduce the following generating series, which is natural to call quantum field. Then Virasoro commutational relations can be expressed in terms of the operator product expansion, and it is equivalent to them by saying that L of x, L of y is equal to derivative of L of y x minus y plus 2 L of y x minus y squared plus c over 2 x minus y to the 4. And of course, if you apply the Fourier transform, this transformation to both sides, then you get the first example, the Virasoro Lie conformal algebra. Which is module of rank 1 plus C of D plus one-dimensional space, and the lambda bracket. In order to define lambda bracket, it suffices to say C is central, so it suffices to say only what is lambda bracket of L with itself. The lambda bracket of L with itself is just D plus 2 lambda times L plus lambda cube over 12 times C. So I've done here what Tony in his lecture called reducing infinite to a finite. So you have infinite dimensional Lie algebra, and you just reduce it to just something one-dimensional. And this is really, in the theory of Lie algebra, this is one of the basic ideas how to classify infinite dimensional Lie algebras. If you have an infinite dimensional Lie algebra generated by finitely many fields, then using this Joseph trick, you reduce it to something finite. And then finite is easier to classify. And indeed, you can classify this kind of objects.
How to see this identity layer and this identity layer? How they are related? It transform with respect to y?
Yeah. If you, no, like this. If you apply to both sides this transformation, you get it. So I want to talk about, there is now a complete classification in super and in non-super and super case of all these finite dimensional Lie conformal algebras and super algebras. There is representation theory. Let me just give you one example of a representation. Yeah, let me put also here. All irreducible representations of this Lie conformal algebra are of rank 1. Let me, and parameters, and are parameters by one parameter delta. And in order to define it, you only have to say how L acts. So L lambda acting on V delta is very simple. It's just D plus delta lambda times V delta. And the Cx is 0.
So what type of representations are the original algebra?
You mean corresponding to this?
Yeah.
It's representation in densities. Representation in it's equivalent. It's the same as representation in terms of Lie algebras. Representation in 1 minus delta density. If you take Virasoro algebra and take its representation on the space, and then translate it into the language of Lie conformal algebras, you get this simple form.
There is actually a two-parameter family, so you can take t to some epsilon.
Yeah, it's true.
They are not obtained.
No, not obtained. You have to. Yeah, so good to have smart people in the audience. You have to add here parameter alpha, which is not very important. You get different representations, but so you have to add this. So if you want to have all representations. But I decided slightly to simplify because now I will say a few words about cohomology, which is really the basic thing that I want to explain. And then there I will skip this alpha, I'll put alpha equal 0. So there is also a cohomology theory, which was, I won't give a precise definition. Let me, so it was developed at the end of the last century by Bakalov, myself, and Sasha Voronov, published in Communications. So it is defined in 2 steps. First step, one defines the basic complex. Say, I don't know, gamma tilde of R prime. And it's isomorphic to a Lie algebra cohomology complex. It's because with every Lie conformal algebra, you can associate canonically certain infinite-dimensional Lie algebra, which in case of Virasoro is just a vector fields of the line, just half of the corresponding algebra. And then you take this Lie algebra complex and then translate it into the language of Lie conformal algebra. But this will not be the right cohomology theory. In order to get the right cohomology theory, you have to take this complex and reduce it by the, so C of D, it is naturally C of D module, and you reduce it by the action of C. So D commutes with the cohomology differential, so we can make this reduction. And then this is the right cohomology complex. But in fact, it's not quite right. It is right only when R is a free module of a C of D. If it is not, then recently with Alberto we discovered that there should be some correction made. Otherwise, it doesn't give the right answer. But it's a kind of technical detail. But in our case, since C is equal to 0, it is a free module, so we can talk about this cohomology. And let me give you an example of what is cohomology of the Virasoro conformal algebra with coefficient in this module and delta. It's not so easy to compute, but we did compute it completely. And the answer is this, that it is 0 unless delta, unless 1 minus delta is one of the pentagonal numbers, and it is equal, and if delta is one of these, then it is equal, dimension is 2 for q equals r plus 1, 1 for q equals r and r plus 1, and 0 for all other. Something like this. In particular, this example shows that cohomology can be non-trivial even when q is equal to 1 or 2 and 2, which tells you that in Lie conformal algebra theory, you cannot go as far as with Lie algebra. There is no complete reducibility. There is no Levy theorem about splitting of the radical. So the theory becomes even more interesting. So you can study extensions of modules.
For q equal r plus
1 for q equals r or r plus 1? Or
For r plus 1, it has two values.
No, if q is equal to r plus 1. Right.
then it is 2.
And second line,
What?
also in the second line, it says q
But
equal
q is
r.
equal r or r plus 1, I think. Or maybe r plus 2, I don't quite remember.
Cannot
But
be
this
r
is a
plus one.
contradiction between two lines.
Yeah, maybe r. But the only thing I want to say is just that it can be non-trivial. So there are non-trivial extensions and so on and so forth.
Are they related to usual extensions or Virasoro or other extensions?
You mean
The
the
usual other
central? No, because you see, if you take cohomology with trivial coefficients, then of course H2 will be non-trivial, and this is central extension. But also other cohomologies are also non-trivial. Okay. All right. So the basic observation that I want to explain today is that this machinery is closely related to a very classical question in variational calculus, and can be solved using it. And let me explain what it is. So the problem, of course, is was studied back by Euler and Lagrange, and it is to find the extremes of the functionals where there are can be several functions. And of course, the answer is that it has extreme if f satisfies a following system of equations: delta f over delta ui is equal to 0. Where by definition, so this is a variational derivative minus d to the n the f du. And for all y. So delta f over delta u, which is a common vector delta f over delta u1, delta f over delta un, is called the variational derivative. Euler-Lagrange variational. I don't know well history at this point, it was long ago really. But there is one observation which probably was already made by Euler, that using the following identity. So here the basic identity which is used, which everybody can easily check for himself or herself. If you take the partial derivative and its commutator with derivative by x, you get the partial derivative by uin minus 1. Of course, which is 0 if n is equal to 0. And from this basic identity, you derive, and this is probably was observed already by Euler, that if you take a variational derivative and apply it to the derivative, so g is d over dx. Of course, these kind of things can be said for arbitrary manifolds, but I will talk about just one-dimensional case. Yeah, Poisson vertex algebra can be developed for arbitrary number of independent variables, but not vertex algebras. Vertex algebras can be done only for one dimension. Yes, Euler's observation is that this is always 0. And proof just uses. And of course, the first question whether converse is true. And then the answer is that it depends what algebra of functions you consider. And the answer is yes, if the algebra of functions you're considering is the algebra of differential polynomials. And I don't know who was first who proved this. In Russia, for some reason, they refer to Gelfand, Manin, and Subin, but I'm pretty sure that it was known to Euler, or maybe to Lagrange. Because more difficult questions were solved in 19th century, so it would be strange that this. All right. So we have to talk about various rings of functions. Of course, you may ask why we cannot just deal with the differential polynomials. And the answer is that there are many interesting equations, and my favorite is Krichy-Vernovitov equation, which live outside of this domain. It is this u triple prime minus a half u double prime squared divided by u prime. So you have to localize by u prime, even in this case. And in this domain, already this is not true, and it's easy to construct, of course, examples. So the problem should be studied in generality of, in kind of more general setup than just differential polynomials. And we found the following setup quite sufficient, a very general abstract setup, which we call the algebra of differentiable functions. It is a differential algebra meaning, of course, that it is a unital, commutative, associative algebra with the derivation. D. In addition, equipped by commuting derivations denoted by d over d uins. There are several i's, and n runs from 0 to infinity, such as the following two properties hold. First, d over du in applied to any function is 0 for only finitely many. N and I. And second,
Not equal to 0.
yeah, it's not equal to 0. And second, the basic identity holds. Actually, only this, with any algebraic manipulations, only this is important, nothing else. All right. So, now what do we have from the from Euler's observation? We have the following map from V, and obviously it suffices to one can define variational derivative in this general setup. A map from V by delta u to V to the L. Just apply variational derivative to element of V using this formula. But by this observation that D applied to something always vanishes, in fact we have even better map, that V mod dV have a linear map from here to here. And this is a very important space in the theory of integral systems. It's called the space of local functions. But now, so as I said, the first question is what is the kernel of the variational derivative? Now the second question is what is the image of variational derivative? And it was Helmholtz who found the necessary condition sometime in 19th century. Which says that if vector, say f, lies in the image of the variational derivative, if it lies, then it satisfies the so-called Helmholtz condition, which says that df, the operator df of d, is the differential operator, metric differential operator, is self-adjoint. Where this is the last piece of notation from the variational calculus, df of d, it is called Fichet derivative. is defined as some right. Ij, it is an L by L matrix, is equals sum over n d f i's coordinate of f d u j n times d to z. And you see that it's indeed differential operator of finite order because by this condition on v, only in the sum only finitely many terms survive. But then how one can restate this Helmholtz observations that if you take this and then map function f to the differential operator df minus df star, you land in the L cross L skew adjoint matrix skew adjoint differential operator. And Helmholtz observation is that the composition of two maps is 0. So it's really a beginning of some complex, which begins with local functionals, and here I wrote the next two terms. And of course, the problem is to find all subsequent terms. And to construct explicitly all the corresponding spaces and write down explicitly the formula for the differential. Okay.
So it's a kind of the rank complex.
Yeah, right.
What is the star?
Adjoint differential operator. You have matrix, take its transpose and to each entry apply the usual notion of adjoint of the differential.
So you can define such complex in any classical field. Yes.
Okay, so what is the usual? Of course, such complexes were discussed quite a bit. But again, I don't know who was the first who proposed construction of it, which I'm going to explain. The earliest reference I know is Sasha Vinogradov.
Before him was Takins 1980. I quoted it a lot in 1981. So at
okay.
that time I knew very well.
But anyway, apparently 1980.
I remember
I think
what was
Vinogradov-
Takins 1980.
I think Vinogradov was in 79.
It was big war.
But anyway, it is rather relatively
I will
reasonable.
tell you details personally.
Okay, so what is the construction? Actually, I learned it from Gelfand and Dorfman, who don't refer to anybody, but and they did it in early 80s. So what you do, as Pasha rightly guessed, you begin with the RAM complex. Namely, you, which I will denote by omega tilde of V. And that is just, you know, the usual thing. Just you take the exterior algebra over V of the space of delta UIS. So its elements omega k of V will consist of elements of the form f d delta ui ur u1 and 1, etc. Delta u I1, u is, and s. And then here, of course, differential is applied in the, again, in the usual way. Delta of delta ui is equal to 0, and delta f is sum df over dui and delta ui. Anyway, you do the thing which just first thing that comes to mind. So there is this complex. And so what is this complex? First you have functions. After that you have one forms. After that two forms, and so on. And the maps are just differentials. But of course this is not what we want, because you want that it begins not with v, but with v divided by dv. And of course the obvious thing to do is just divide by dv. Namely, the partial derivative of d acts on this complex and commute with d and delta. So one can consider the reduced complex. which is denoted by omega of v, which is v divided by dv, goes by omega tilde 1 of v divided by d omega 1 of v, and so on. And it is pretty easy to see that this space is indeed canonically identified with v to the l. But after that somehow, and this map then, after this identification, is indeed delta over delta u. So at least as the first step, it is the right thing to do. And it turns out that it is this is the right complex. And what I want to explain is two things. First of all, give some conditions when this complex is exact, which would cover situations like the Krichy-Vernovikov equation. And secondly, how to construct it explicitly, not as a quotient of some larger complex. In particular, of course, this will be omega 2, and then the next terms also I will explicitly describe. So the answer to the first question, when it is exact, is given, as I said, it's exact when V is algebra of differential polynomials. But let me give you some conditions when it is exact in a much more general situation, which actually gives more or less a complete solution of the problem. Namely, this V contains, admits a natural filtration by subspaces V and I, which consists of elements such that partial derivative of f is 0 for the pair Mj greater than Ni is the lexicographical ordering. And now the basic definition here is V, this algebra, or I erase the definition, this algebra of differentiable functions is called normal if d over dun maps V and I on itself surjectively. Of course, if it is not normal, it can be made normal by adding a certain number of integrals. And our theorem says that indeed you can make any exact form, any closed form exact if you add finitely many integrals. So let me state it. The complex omega of V is exact if V is normal. And moreover, as I said, having any closed form, it can be made exact by adding finitely many integrals.
Except
What?
except at C.
Yeah, except by exact I mean that all cohomology is 0 except at 0 when it is just constant.
You mean finitely many for any
For any given,
component,
yeah,
or
for any given cocycle.
In general, it will be infinitely many.
Yeah, yes, but for each given, it will be different. Right. So this is the first theorem. And the second theorem is a description of the complex of the explicit description of the omega. So the complex omega of V, which is V mod dV, going to V to the L, going to skew-symmetric differential L by L differential operators. Yeah, maybe I should say just in general. So it is just this will be omega 2, omega 3, and so on. So I have to say what is isomorphic to the following complex. So I have to say for k greater or equal than 2, for k greater or equal than 2, omega k of V is the space of all differential type maps of HKV to the space of local functionals and differential delta is as follows. So if you have a cochain S of no, so V to the L of P1, etc., Pk plus 1, so where Pi's are vectors from V to the L, then the differential sum Z from Z is actually pretty simple. So I have to explain first notation. What is xp? xp is what is called evolutionary vector field corresponding to the vector p. It is the following derivation. And these vector fields are all which commute with D, and this is in the theory of integrable systems called the evolutionary vector fields. Maybe I should explain why omega 2, which is supposed to be skew-symmetric operators, is indeed exactly of this form. It is because if you have a differential operator D, then the corresponding map to it, which I denote by SD, applied to P1 and P2, is simply P2 SD P1. And of course, as usually in the theory of integrable systems, integral means the canonical map from V to V mod D. So this identifies skew-symmetric differential operators with this kind of maps. And the main statement is that all other spaces are similar, and the differential delta can be written down explicitly in this form. Okay, so what are the corollaries from it? Of course, the first two corollaries is go back to Euler and Helmholtz. The first says that delta f over delta u is equal to 0 if and only if f is equal derivation applied to g plus a constant. And this constant, of course, contributes to the fact that H0 is one-dimensional. Secondly, f lies in the image of the variational derivative if and only if df is self-adjoint operator. Of course, both are provided that V is normal. But as I said, if V is not normal, one can always add some integrals. So G is not exactly in V, but it's some finite extension of V by some extension of V by some finitely many integrals.
Now you say that is every component in your, you have this gradation of filtration. In any component of filtration is finite.
Right.
In general, it's infinite for me.
No, but since each function depends on finitely many variables, you have to add only finitely many integrals because you go down by finitely many steps. Maybe I should say that this condition of normality is used in order to construct certain homotopy operators which allow you to go down this filtration step by step. So the proof is very easy. Yeah, of course, this proof exactness of omega tilde, and exactness of omega follows by the long exact sequence in cohomology. All right, so finally, one more corollary which is very important for the theory of integrable systems, namely when, as I said, the two cocycles consist of skew-symmetric differential operators. And among them, the most important are closed as skew-adjoint differential operator S is symplectic. it satisfies some condition which I'm going to write. If and only if S of D is equal to df minus df adjoint, which I will denote by SF. So it's a complete classification of symplectic differential operators. So for each vector f in V to the L, you have you can construct a symplectic differential operator, and these are all. I will write down what symplectic means in a moment, but let me just give you some examples. S1 divided by U prime and S1 divided by U prime double prime. These are the most famous symplectic operators. They were discovered respectively by Sokolov and Dorfman, which allowed to prove integrability of this Krichever-Novikov equation. All right, I have, hope, 5 minutes to explain what does it have to do with cohomology, Lie conformal algebra cohomology. So we have to introduce Lie conformal algebra and its representation. And the claim is that, okay, let me state it. So theorem the complex omega delta is isomorphic to don't remember, I think I used notation gamma. Gamma of R M R V, where R is this Lie conformal algebra with trivial lambda bracket. And the representation on V is this UI applied to F, lambda applied to F is sum df dui n lambda to Z. Again, it is polynomial since there are infinitely many derivatives can be non-zero. So this isomorphism is completely canonical. One can write explicit formula. But how the previous theorem follows from this one? It is because for any the complex gamma RV can be described explicitly for any conformal algebra and any its representation. Yeah, I plan to describe it, but I think, let me just say one word. It turns out that this is again closely related to lambda brackets, namely gamma. We know what is gamma 0 and gamma 1 is the same as before. And gamma 2 consists of, indeed consists of lambda brackets, A lambda B. such expressions which satisfy the first two conditions, sqlinearity and sq-commutativity. And in order to construct further terms, you have to introduce lambda mu brackets where you have two parameters, and so on, which also satisfies sqlinearity and sq-commutativity. And one can write down explicitly the differential and prove that this is isomorphic to this reduced complex, I think I already erased. And if you go to the special case when Lie conformal algebra is abelian and it's given by this particular formula, then you discover this formula given from the theorem. Yes, and I promised you the final thing. I promised you to write down what does it mean symplectic. It can be written in this language. It just says that in terms of this representation, symplectic if ui lambda skj minus uj mu ski plus all right, thank you. My time is up.
Thanks very much. Questions? Dates.
Maybe I should make a little advertisement. Alberto De Sole will now give his talk where he will explain how the machinery of lambda brackets leads to Poisson vertex algebras and how they apply to proving integrability of evolutionary, Hamiltonian evolutionary equations.
Well, the question is the following. Usually in integrable systems, people consider by Hamiltonian or vice, system. And there is a condition of, that Hamiltonian structure is compatible.
Right.
And same, there are similar conditions for symplectic structures compatible. And there is a question, for instance, how to say that symplectic and Hamiltonian structure compatible. Is it can you comment it on in this term of your complex?
Yeah, of course. So this is basically what Alberto will be explaining. Let me just say that compatibility of two Hamiltonian structures simply means that linear combination of two lambda brackets is again lambda bracket satisfying all these axioms.
But how to make how to answer the question whether Hamiltonian is symplectic structure compatible?
But isn't you can on a usual manifold you can invert symplectic form and you get a Poisson.
No, you see here
Yes.
is
And then you
vertex
can
is-
say that
is-
compatible.
is-
That's very,
no. So basic
it's a
idea
very
is
efficient way to check. I would say.
the basic idea is that both Hamiltonian and symplectic are special cases of more general thing, which is called the Dirac structure.
Yes.
And then one can talk about compatibility of any two Dirac structures.
But he's asking if there is an easy way to check.
Yes.
But it is more difficult than in the Hamiltonian case.
You mean the book of Dorfman?
Yeah.
All right. More questions? Thank you. Once again, thanks very much.